So it takes work to turn that wire, okay? And the work you put in is converted to electrical energy, okay? So in a dam, flowing water turns that wire. In a windmill, the wind turning the blades turns these wire, which gets converted to electrical energy. So the energy in the wind gets converted to electricity. In a nuclear power plant, what happens? You split nuclei, heat is produced. From the heat, you produce steam, which is turning this wire. In a coal power plant, what happens? You burn coal, produce steam. The steam is turning this wire. So all the work that you do in turning this wire is turned into electrical energy. Okay, you can produce electricity like this in solars. So use. Okay, I gotta go get a tissue. I'll be back in a second. You can go sign in. All right, so you saw that using Faraday's law, where you're turning that wire, you can produce electricity. Photovoltaic cells produce electricity in a different way. Okay, so this technology is a little harder to understand. So you can produce electricity two different ways. You can produce it using photovoltaic cells, or you can produce it trying to turn that piece of wire. And how do you do that? Here's what you can do. Okay, so you can do this. See, these are mirrors. What are these mirrors doing?
Reflecting the light.
They're reflecting sunlight and heating salt in this thing, in this tank. So all the heat is stored in this salt, molten salt, and then you extract the heat, boil water, produce steam, and what do you do with the steam?
You
Turn that piece of wire. So that's two different ways of doing it. Okay? This is called concentrated solar power. Concentrated solar power. Okay? So you're concentrating solar energy, heating that salt, and producing electricity. Okay? So those are the two technologies that we have. Okay? We'll go over all these slides. Okay, so this tells you renewable energy costs. This is concentrating solar, and that is about 10 cents per kilowatt hour. Here's photovoltaics. Okay, the price is about half with photovoltaics. So why would you produce electricity like that? But we do that. Why do you think we might produce electricity like that?
It's expensive.
Yeah, so it's expensive. Why would you do that? Why would you pay twice as much? Do you guys understand the question?
Yes, again?
Hmm?
So eliminates the need for batteries?
I'm sorry?
It eliminates the need for batteries?
The hell eliminates the need for batteries. Because when you heat that salt you can maintain it hot throughout the night, and you can produce electricity at night. The photovoltaic cells cannot produce electricity. You produce electricity during the day, and you'd have to store it in the batteries for night use. Okay, so everything has a need. Okay? All right. So those are the two technologies for harnessing solar energy. What is our goal? You use you capture sunlight and you want to convert it into electricity. So the two technologies are you heat salt, and from the hot salt, from the molten salt, you extract that heat. You pass water through it, convert it into steam, which turns the turbine, which produces electricity. And the other way to produce electricity is, you guys have seen these photovoltaic cells, and sunlight falls on these panels, and it's converted directly to electricity. Again, now understanding that will be probably one of the more complicated things we'll be doing. So you will, if you want to understand that, you'll have to be a little patient, and we'll get to that um, maybe next lecture. Okay. All right. So that's where we're headed. Okay. So let's go over the slides. Okay. So as we saw that it takes 16,000 Hoover dams to run the world, and there's plenty of sunshine falling. There's plenty of wind blowing in, where we could use just these two technologies to run the world. Okay. Between these two and nuclear reactors, you can have a zero carbon footprint um, way to run the world. Here's another advantage of solar and wind. Okay. Let's say I have a coal power plant, a nuclear power plant, a solar power plant. Okay. For coal, 10 years from now, I still have to pay for coal. There's a fuel cost always. For nuclear, also there's a fuel cost. But for solar and wind, there's no fuel cost. Okay? Once you set up the plant, you run it for free. What is the disadvantage? I mean, the sun is not shining all the time and the wind is not blowing all the time. Okay? You guys remember the efficiency, or what was the term? I forget the term. A nuclear power plant is running 95% of the time at full capacity, the capacity factor. Anybody remember what it is for solar and wind? It's about 25%. Okay. So what that means is, let's say you invested $10 billion in this thing, your $10 billion is working 95% of the time. Your solar energy, if you invested $5 billion on that, solar is much cheaper, nuclear is much more expensive, it's working 25% of the time. Okay? So the capacity factor is low, but anyway, all in all, this works out to be the best. Okay? All right, so solar power is a renewable source that can easily fulfill the world's energy needs by itself. Okay. So total solar energy reaching Earth's surface is 9 times 10 to the 16 watts. So this is all the time. And so even at the photovoltaic efficiency of 15%, so what does that 15% efficiency mean?
You guys not harnessing that much?
I'm sorry? Yes, so if 100 units of sunlight falls, 100 joules of sunlight falls on the photovoltaic cell, 15 joules is converted to electricity. That's what that means. When you go, so we do much better than that. I mean, nowadays you can buy the ones that you see on rooftops and stuff like that. Those are about 20% efficient. So even with a photovoltaic efficiency of 15%, world power can be fulfilled by harnessing only 0.1% of the sunlight falling on Earth. Okay? 1 part in 1,000. That's all you need to do. Harness 1 part in 1,000 of the sunlight falling. So the only problem is if you only had cheap batteries for nighttime power, the world could be run on solar alone. Okay. So if you want to become a billionaire or a trillionaire, go invent a cheap battery. Yeah. So by the way, in a net zero scenario, the world would need about 1,000 gigawatts of solar storage technology. What does that mean? A gigawatt is a Hoover Dam. So 1,000 Hoover Dams worth of batteries. You know, to be able to store that for several hours. Okay. Here is a Stanford University group projection. Okay, so by 2050, they say that with current technology, you can run the world entirely on renewables. Okay. And what they're saying is all you need is 12 terawatts. That is 12,000 Hoover Dams. Today we are running the world on 16,000 gigawatts or 16 terawatts. And what these guys are saying is in 2050, when you're running the world on renewable alone, all you need is 12 terawatts to run. In the future, in 2050, 25 years from now, you need less electricity to run the world. Less energy to run the world. Why is that? What's going on?
More efficient?
Why is it more efficient?
No, we're going to be more efficient, so we're going to use less electricity.
And so, well, what is happening today, we're using a lot of fossil fuels. What's the problem with fossil fuels? You burn the fossil fuels, the heat produced, only a third of that is converted to electricity. Okay? What happens to the other 2/3? It's just thrown out the window. Okay? But with renewables, if you produce electricity, electricity is very efficient. So for instance, when you drive a gas car, only 20% of the energy is converted to motion. In a battery car, 90% of the energy stored in the battery is converted to motion. So your electric car is 90% efficient. Okay? Your gas car is only about 20% efficient. So anyway, things running on electricity are more efficient. So you can run the world on 12,000 Hoover Dams. Again, now this is before AI came and all that stuff, but that's so anyway, that's a different story. Okay, so this group predicts here's where the energy would come from. Okay, so onshore wind, about 3,000 Hoover Dams. So a terawatt is 1,000 Hoover Dams. Okay, so onshore wind would be 3,000 Hoover dams. Uh, Offshore wind would be 1,500 Hoover dams. This is photovoltaic solar would be 2,500 Hoover dams. CSP is concentrated solar power. Okay? So that you saw that reflecting mirrors, heating salt, and all that. That would be 1,500 Hoover dams. Okay? Why would you build those? Again, so you don't need batteries to provide electricity during nighttime. Okay, residential photovoltaics, so everybody having rooftop solars and stuff like that, that would produce about 2,000 Hoover dams worth and so on. Okay, so the world can be run on renewable alone. Okay, and this is, you don't have to invent new technology, just with existing technology. Okay, and as as technology gets better, things will get cheaper. Okay. So at least you know, we know that the problem is solvable. Okay, that's the big thing. Okay. All right. So here's this is what is called a Stirling engine. Okay, and what is this doing? It's reflecting sunlight and it's heating stuff, and which runs the engine. The heat runs the engine, and that engine can turn the wire to produce electricity. Okay, so this is turning a wire between magnets to produce electricity. So that's how you're converting heat to electricity. Okay, solar radiation to run heat engines to drive a generator. Okay, so you can use solar engines to run a heat engine which will drive a generator. Driving a generator just means turning that piece of wire. Yep. Or you could produce electricity using photovoltaic devices. Those are photovoltaic cells, and we'll talk about that. So that's a little complicated story. Concentrated solar power capacity. Concentrated solar power capacity. So what you're doing is you're concentrating solar energy. Here again, what do you think is being done here? Just look at.
Is the water being heated?
Yeah, so what you're doing is you're passing water through this pipe, you're heating the water, producing steam, and what is that steam doing? Turning that wire. Okay. So those are all concentrated solar, well, okay. So global concentrated solar power capacity is, this is in megawatts of electricity. Megawatt is a, so 6,400 and 6,400, I'll say 6,500 megawatts. This is 6.5 gigawatts. Mega is 10 to the power 6. This is 10 to the power 6. This is 10 to the power 9. So 6.5 gigawatts. What is a gigawatt? I'm sorry? A Hoover Dam. Okay. So this is 7 Hoover Dams worldwide. That's nothing. How much do you need to run the world? How many Hoover Dams do you need to run the world? 16,000. Okay. So this is a drop in the bucket right now. Okay. Yeah. The photovoltaic capacity is this is 1,000 gigawatt, and that's and again, to run the world you need 16,000 gigawatt. Okay, so the photovoltaic capacity is increasing tremendously, and that's because it's cheaper, and so right now we're just using it right as we're producing it, okay? Because batteries are still expensive. All All right, why is this photovoltaic installation exploding? You can see that the capacity is increased tremendously. Every year we are building about 70 gigawatts every year. So here's another. How long do you think it'll take to build a build a Hoover Dam? Now, a lot of money in 20, 30 years probably. Look at this. We're building 70 Hoover Dams worth of photovoltaic capacity every year. This is photovoltaic panels are easy to install. Okay, this is very easy to do. So why is that happening? See, the cost per watt of photovoltaic cells has decreased tremendously. Back in the 70s, it used to be $100 a watt. And only NASA could afford it for their space flights and stuff like that. For their satellites, they would install solar panels and stuff to produce electricity. Now you can do that on your rooftop. Okay? So the price has come down tremendously, and that's why we're starting to use solar cells. Okay? So today the price of solar cell per watt is about 30 cents for large-scale installations. Okay. What does Mr. Swanson say? And this is basic economics. If the price of something goes down, what happens? The use goes up. Okay, so so average module price, as the price is going down, the total shipment is going up. Okay. And the graph shows a log plot of solar module price versus cumulative module shipment. Installation cumulative. So as the price has dropped, the cumulative installation has gone up. Okay. So now we'll talk about the easy way of generating electricity from solar energy. You use solar heat engines. Okay, so here's a parabolic trough. So thermal systems use concentrating collectors. So here's a collector to focus sunlight to produce high temperature fluids. The high temperature, so this is a Stirling engine. This is not producing high temperature fluid. The high temperature fluid can be used for electricity generation. You can use it for industrial processes and other processes as well. Okay, so so here is a parabolic trough. So this is in California. Working fluid is heated by circulating it through a pipe at the focus of the parabolic trough. Okay. Steam produced using this heat can turn the wire in a generator. Okay. So efficiency is limited to about 15% for these cases. Okay. What does that mean? Only 15% of the heat collected is turned into electricity. What is the efficiency of a coal power plant? About 35%. So as nuclear is 35% and so on. Okay. So this efficiency is low because the fluid is not being heated to a high enough temperature. Okay. So this is what is called a Stirling's engine. Okay. Again, the heat collected heats a plate here, which drives the engine, which turns a wire in the generator, In the Stirling engine, efficiencies of about 26% have been achieved in commercial installations. Okay, so 26% efficiencies have been achieved. The advantage of a Stirling's engine is there are fewer moving parts, and all you need is gas to run them. Okay, so these are long-lasting engines. heat of working fluid to run a heat engine to produce electricity. Have Has anybody seen something like this? Okay. So, um, okay, so these are tracking mirrors as the sun moves in the sky. These mirrors turn and they're reflecting sunlight into this tank. Um, and nowadays you use molten salt. You use salt and you melt the salt. Okay, so here's the deal with the salt. What you want is you want a mixture of salt that is molten for the longest temperature window. So let's say uh, there's a mixture where the salt is molten from 131 degrees to 500 degrees. Okay. Okay, what is the advantage of this? The salt you can insulate, and the salt can retain its heat for up to a week. Okay, so it eliminates the need for batteries. Okay, and the longer the window, the wider the window the salt remains molten, the more heat you can extract from it. Okay, so let's say if the salt became solid at 200 degrees Celsius, then you extract less heat from it. Okay, so what you want is a mixture of salt that is molten over a wide window of temperatures. Okay, so that's what you're looking for in that system. Okay. So early designs heated water and used the resulting steam to power a turbine. The problem with heating water is the steam doesn't retain heat over long periods. Okay, it'll condense and stuff. So you can't. A salt will remain hot overnight and stuff for a longer time. Okay, so newer designs use molten salt to store the collected solar heat, which can be used to operate a generator. You know? So molten salt is used in solar power systems because it's liquid at atmospheric pressure, provides low-cost medium to store thermal energy. Its operating temperatures are compatible with today's steam turbines, and it's non-flammable and non-toxic. So these salt storage systems have many good properties. They're non-toxic, and the salt is molten at the correct temperature and all that. Okay. The first commercial molten salt mixture was a common form of saltpeter, 60% sodium nitrate and 40% potassium nitrate. Okay, so saltpeter melts at 220 degrees Celsius and is kept liquid at 290 degrees Celsius in an insulated storage tank. Calcium nitrate, so if you add this, can reduce the melting temperature to 130 degrees. See, you're trying to widen this temperature window. Okay? The higher the temperature it can go, the more efficiency, the more heat you can store. Okay? And the lower the temperature, the more heat you can extract. Calcium nitrate can reduce the melting point to 130 degrees, permitting more energy to be extracted before the salt freezes. In addition, now there are several technical calcium nitrate grades stable at more than 500 degrees Celsius, allowing more heat to be stored. Okay. The limit to going to higher temperatures, you don't want the salt to degrade or dissociate. Okay. Okay, tanks that power a 100 megawatt turbine. Okay, so what is 100 megawatt? 1,000 megawatt is a Hoover dam, so this is a tenth of a Hoover dam. For 4 hours, the tanks that power a 100 megawatt turbine for 4 hours would be about 9 meter tall and 24 meters in diameter. So this tank would be as big as this room and twice the height of this room. Okay, that's pretty good. And that's producing electricity at a tenth of a Hoover dam for 4 hours. Okay. So remember, what is the advantage of these guys? What is the biggest advantage of these guys?
No battery.
No batteries. Okay. On July 4th, this is several years ago, a company in Spain celebrated a historic moment for the solar industry. Torresol's 20 megawatt concentrating solar power plant became the first ever to generate uninterrupted electricity for 24 hours straight. Yeah. You're using a molten salt heat storage facility. All right, so given that you don't need battery, this is the extra expense is worth spending. Okay. So concentrating solar is the most expensive of renewable sources. Onshore wind is the cheapest. Okay, and then then photovoltaic, they're neck and neck. Offshore wind is a little more expensive. But why would you build offshore wind farms?
So it's out of the way?
What's that?
So it's out of the way? It's more consistent, right?
The more consistent and faster wind.
So hard to maintain though, right?
What's that?
Hard
It's
to-
harder to maintain. It's rough on the salt water is rough on the thing, but you can factor all of that in. What is the biggest advantage of all these guys?
Clean energy.
No fuel costs and no carbon footprint. Okay. In a net zero scenario, the world would need about 1,000 gigawatts of storage technology. The molten salt heat storage system, the need for batteries is eliminated, making them a viable solution in many situations. All right, now, so we've learned the first way of producing electricity from collecting solar. Okay, now we're going to learn how photovoltaics work. Okay, and it's a slightly complicated story. So what I'll do is I'll just give you a brief introduction to it, and then we'll talk about it next week. Okay. So here's a model of an atom. Okay, this is the nucleus. These are the allowed energy levels for allowed orbitals for electrons. Okay, how many orbitals are there around an atom?
In this one or
Hmm?
general?
I'm sorry?
In this one or general?
In general, around every atom, how many allowed orbitals are?
Is it 8?
It's infinite. Okay. How when you build an atom? So let's build an atom. Okay.
The S shell, and
What's that?
the S shell, and shell.
Oh, well, those are subshells. Okay.
Oh.
Okay. So let's build an atom. What do we build? Let's build carbons. Okay. Let's build carbon. So what does the number 6 tell you?
It has 6 atoms. I mean, 6 electrons.
It has 6 protons and
6 valence electrons?
and 6. No, they're not all valence. It has total of 6 electrons. Okay. So here's 4, 5, 6, and then this guy C6, 12. So 12 tells you the number of protons and neutrons. So this guy has 6 neutrons. Okay. So 4, 5, 6. Okay. So now to make this, the electrons are in these shells, in these orbitals. Okay. This is the n equal to 1 orbital, n equal to 2 orbital, n equal to 3 orbital, and there's an infinite number. Okay. Now what do you do? This carbon atom needs 6 electrons to make it neutral. So what you do is you fill the electrons starting from the lowest energy level. So this is the lowest energy level. And this is one, so this has sublevels. This has only one S sublevel. This has two S sublevels and two P sublevels. Okay, so this guy can hold 2 electrons. Okay, how many more electrons do you need to put? 4, and that has to go in the next higher energy level. Okay, this guy has the level sublevels are 2S and 2P. The S level can hold 2 electrons, and P levels can hold 6 electrons. Okay, so 2 electrons in the S level and 2 electrons in the P level. So there are the 4. Okay. So the electrons in the outermost shell, those are the valence electrons. Okay. In chemistry, that's all you're messing with. You're never touching these guys. All you're doing is rearranging these valence electrons. Okay. So for instance, what does an atom want to do? It wants to either have an empty valence shell or a full valence shell. Okay, so let me give you an example. So fluorine, now I'm going to draw simple models. Fluorine is, what is fluorine? Atomic number 9. So it's got 6, 7. There's fluorine, and lithium is 3. Or I'll draw lithium. That's easier. This is lithium, 2 electrons. Okay, this is fluorine. How many electrons does it have in the valence shell? I'm sorry? 7 in the valence shell. Okay. An atom likes either a full valence shell or an empty valence shell. A full valence shell is 8 electrons. Okay. So what's fluorine's goal in life?
Just to fill the outer shell.
To get 1 electron any way it wants, any way it can. What do you think this guy's goal in life is?
He wants to get rid of.
There you go. So all those guys on the left, so the first column guys have 1 electrons in the valence shell. So all they're doing in life is trying to get rid of that electron. The guys on the right, not the noble gases, but the column before that, fluorine, chlorine, and all. How many? The halogens. How many electrons do they have in their valence shell? 7. So those guys are talking to these guys. Huh? Yeah. That's what. So those will react with those guys. Okay. These guys on the left want to give up electrons, and those guys on the right want to. Okay. Want electrons, so they're happy talking to each other. All right. So here are these electronic shells. Okay, so now what we'll do is the photovoltaic cells are built from silicon. Okay, silicon is the atom below carbon. It has 14 electrons. Okay, so let's I will build the silicon atom. Okay, so 2 electrons, and then eight, and then that's 10, and then 4. Okay, so it has 4 in the outermost valence shell. So silicon wants to, it's halfway in between. It tries to get 4 more electrons and stuff like that. Okay, so it's a semiconductor. What is okay? Now here's the deal. So here are some basic things you need to know about. So here's an electron in a lower orbital. You can excite this electron when it absorbs a particle of light. This is called a photon. When a photon is absorbed, if the photon has the right energy, it can excite this electron from here to there. And generally, this electron will go back to its ground state by emitting the photon within a billionth of a second or a trillionth of a second. So it happens very fast. Okay, so you can excite. So now here are these energy levels written like so, increasing energy. So when you shine this photon, the electron got excited from here to there. Okay. These are the energy levels. The energy levels, so n is remember the number of orbital. So the orbital quantum number. Okay. So here are the energies in terms of the orbital quantum number. Okay. So so here's the first quantum number, n equal to 1, n equal to 2, n equal to 3. Each n has orbital angular momentum numbers. So each n has sublevels. This has one sublevel, and the sublevel is called S. This has two sublevels, S and P. This has three sublevels, S, P, and D. Those the sublevels are named S, P, and D. Those numbers tell you what is the orbital angular momentum. Okay, so this has three sublevels and so on, four sublevels and so on. Okay, so in multi-electron atoms, electron-electron interaction causes energy level to be split based on the electron orbital angular momentum. Okay, so generally, if the electrons didn't repel each other, all those sublevels would have the same energy. Okay, the energy would only depend on n, but those energy levels get split up. Okay, so what this is showing you is, see, the n equal to 4 level. So it has four sublevels, S, P, D, and F. Okay, and the 4F levels have the highest energy. Okay. All right, so that's the structure of the atom. Okay, so here's silicon's electronic structure. Okay, so I drew this silicon atom. Okay, so this is the lowest level. This is 1s level, which has 2 electrons. 1s2 electrons. So that's the notation. Okay, 1s2. Then the next level is, this is n equal to 2 level. It has n equal to 2, and it has 2s and 2p sublevels. The 2s level has 2 electrons, 2p has 6 electrons. 2s has 2 electrons, and the p level, 2p level, has 6 electrons. And then this is n equal to 3. It has 3s level, 3p level, and 3d level. Okay. The 3s has 2 electrons and 3p has 2 electrons. 3s has 2 electrons and 3p has 2 electrons. So that tells you how the electrons are distributed in the silicon atom. Okay, so 1s has 2 electrons, and again, don't worry about all the details. It's just that when you're building an atom, you're filling electrons from the lowest to higher energy level. You fill, how many electrons can you put in a level? I mean, there's a limit to how many electrons you can put in each level. You keep filling them, and then you keep going to the top. Okay, you can't put all electrons in a single level. Okay? Electrons are fermions, and every electron has to have a unique quantum number. Okay? So you can't put more than one fermion in a given quantum state. Okay? So this is how the electrons are arranged in a silicon atom. This is for a single silicon atom. Now, when you make a photovoltaic cell, like this is a crystal. You make it out of a crystal. There are billions and billions of atoms. Okay. So here's what happens. So for a single atom, these are the energy levels, right? And now, when you put together a crystal, these are all atoms. And let's say there's a billion atoms here. Each energy level will become a band. Okay? And this band will have a billion sublevels. Depending on if you have a billion atoms, there'll be a billion sublevels. Okay? So, okay, you just have to be patient with this. Okay. So there are the energy levels of a single silicon atom. And then when you put together a crystal, all those energy levels became a band. Okay. This is a completely full band. This is an empty band. When you shine light on that crystal, that light photon can be absorbed and it can excite an electron from here to there. Okay? So for instance, so that's what's shown here. See, a light photon shines on it. An electron can be excited from a lower level to the higher level. Okay, you shine a photon of light. This electron got excited to there. Okay? And it left behind a hole. This hole acts like a positive charge. An electron is a negative charge. What does a positive charge do to a negative charge? It attracts it. So you shine this photon, this electron got excited, and it wants to immediately fall back. Okay? What we want to do is, we want to take this electron and pass it through your electric bulb, and then come here. You want for it to do something, not lose its energy immediately. Okay, and now how to do that, that's the billion-dollar problem. And that sort of won a Nobel Prize. Okay, and we'll talk about that. Okay, did you guys understand that? So so an electron can jump from a lower energy level to a high energy level by absorbing a photon. The electron goes back to an empty lower level by emitting the photon. So it can go back to the lower level by emitting that photon. In semiconductors, the highest occupied band is generally full and is called the valence band. The next higher band, which is empty initially, is called the conduction band. Okay. In principle, the electron, when sunlight falls on the photovoltaic cell, and this electron is promoted to the conduction band. In principle, the electron and hole could flow through an external circuit. What you want is to flow through an external circuit, for instance, your toaster, and make your toast. If that's what you want it to do, instead they fall together and waste that energy. The sunlight that was absorbed is re-emitted. In principle, the electron and hole could flow through an external circuit providing an electric current. However, because of their attraction, they recombine instead almost always. The electron-hole pair in a pure silicon crystal would recombine within a billionth of a second. Okay, so sunlight fell, this got excited, and they recombine within a billionth of a second. Okay. Now, how do you prevent that, and how do you make this flow in an external circuit? Okay. So that's the problem we'll talk about next week. Okay. And I mean, that thing won a Nobel Prize. And that's called a PN junction, and we'll talk about that. Okay. So we're going to talk about how photovoltaics produce electricity. Okay. And they're the only technology where they're not turning the wire. Okay.